Good morning. Today's lesson is about particles which are called fundamental. Fundamental particles are sometimes known as elementary particles. Okay, so what is a fundamental particle? Let's go back and have a look at something we did earlier, which is electron-electron collisions, where two electrons are collided in some sort of particle collider. And we noticed, not we, you and I, but physicists have noticed that all that happens is that the particles annihilate each other and produce bursts of pure energy. There are no other particles formed in that collision. So if you collide particles and you only get energy released, then that's what a fundamental particle is. So a fundamental particle is a particle that cannot be broken down into smaller parts, and electrons are a very good example of a fundamental particle. So fundamental particle cannot be broken down into anything smaller in terms of a particle. Only do you get energy being released. Okay, another little bit of revision is beta decay. You remember that a neutron in the nucleus of an atom can decay into a proton, which stays in the nucleus, and an electron or beta particle that is emitted. Obviously, the beta particle is an electron, so therefore a beta particle is a fundamental particle. At the same time, we get an antineutrino emitted. An antineutrino is also a fundamental particle. So beta decay, we've got our electron, and we've got, just going to move that across a little bit. I'm going to build up a table, so you need to keep a little bit of space here, and our antineutrino are produced at the same time. Now, don't forget, we've got antimatter particles as well. So when we have positron emission, that is associated also with a neutrino. So these two here are matter particles. These two here are antimatter particles. Don't know why I did that one in red. Antimatter particles. These are our two neutrinos, and these are our two different types of electron, a matter electron in blue and an antimatter or electron or positron in red. I knew there was a reason for doing it in red. Okay, so we've got four particles. Now, as physicists spent more and more time smacking things together, electrons together, they were still trying to break them apart. So they thought, right, what do we need? We need a bigger hammer. So a bigger hammer just means that you collide electrons together with more energy. You make them go faster in a particle collider. But it didn't matter how fast the electrons were collided. They only annihilated each other and gave pure energy. But they did find at higher energies another couple of particles and their associated neutrinos came into existence. And so this family here, this is like a sort of low energy family. These are things that exist around us, and they're almost, well, electrons certainly are observable. The antineutrinos are observable because they're produced all the time in nuclear decay that goes on around us. Positrons are also a low energy particle. along with the associated neutrino. But at higher energies, we just find we get the same particles, but in a heavier version. Now, why a heavier version? Well, if you remember, we've got E equals mc squared. At low energy, small energy, we have small mass particles, and these particles are all small mass particles. If we collide particles with larger energy, we get larger particles. And it's possible to get a new family of particles which are basically all exactly the same, but just heavier. So a larger version, a larger, heavier version of an electron is called a muon. And it's just a more high energy version of the electron. It has exactly the same charge, minus 1.6 times 10 to the negative 19, but it just has a larger mass. You don't need to know what the mass is. You can certainly look up the mass of an electron on the data sheet, but you wouldn't normally find the mass of a muon. Now, these higher energy particles are normally pretty short-lived, so we don't normally see them. So they're not sort of normal world particles that are around us. However, they are naturally formed in what are called cosmic ray collisions in the upper atmosphere. You don't need to know too much about this, but it's of interest. So what are cosmic rays? Well, cosmic rays were thought to be rays of energy, but they're in fact not. It's a complete, what's called a misnomer, complete incorrect name. And cosmic rays are actually particles, the vast majority of which are ejected from the sun. And there's a huge stream of particles leaving the sun every single second, enormous numbers of neutrinos and electrons and protons are just sort of boiled off in the incredibly high temperatures and fusion reactions that go on in the sun. And these particles make up something called the solar wind, and they spread out in all directions away from the sun. And some of them may eventually collide with the Earth. Well, they don't necessarily collide directly with the Earth because we've got the atmosphere above us. So if these cosmic rays come in, here's our atmosphere, and if we get a cosmic ray, which I said is not a ray, it's a particle, comes in and it collides with either an oxygen or a nitrogen atom. These are the most common elements in our atmosphere. And there are a lot of them in the upper atmosphere where the cosmic rays come in. Cosmic rays can't penetrate very far because the atmosphere actually blocks them out when they have these collisions. When these particles collide with atoms of oxygen or atoms of nitrogen, then that's just like an enormous, great big natural particle collider. And muons are quite often produced and they shower down to the Earth's surface, and we can measure how many of them arrive. There's an interesting time with our dynamic universe in that these muons are quite short-lived, but because they're moving so very, very fast, time moves much slower for them. So in the slower time, they can move further. They ought not to get to us. They ought to just decay in the upper atmosphere, but because of length contraction and time dilation, some of them do actually reach the surface of the Earth. And you can look this up. There's some interesting videos that were done on muon decay and special relativity. You can look up some of those. Mount Washington was where a very famous experiment took place, where Mount Washington is one of the highest mountains in the United States, and so it's quite high up in the atmosphere, and you can measure some of these muons in the upper atmosphere. I was lucky enough to go and see a repeat of this experiment, which is carried out on Cairngorm. Cairngorm's high enough that you get more muons arrive at the top of Cairngorm Mountain than you do down in the valley. That's an aside. There's a lot more about this actually in Advanced Higher, and these collisions and the particle interactions that take place lead directly to aurora, which are the northern lights that you can see on very clear dark nights in the winter as a sort of greeny reddish glow up in the north. So natural particle colliders would be these cosmic ray collisions in the upper atmosphere, or down here on Earth, we can actually build particle colliders, and we'll be doing a whole section later on particle colliders and trying to get particles at higher and higher energies to collide. So this is the electron family. Or the first family, the sort of low energy one. The next one is called the muon family. And these particles all have symbols. So what have we got? We've got muon, and we've got its anti-neutrino friend, which is a anti-muon neutrino. And some of these names get quite complicated, and the symbols are quite complicated. Remember, the bar across the top means it's an antiparticle. The sort of V-shaped symbol should actually be more like that with a sort of tail on it. The V-shaped symbol is the neutrino. So these two are caused in exactly the same way as these two. Now, if you take the anti-muon with the bar across the top, it decays with a muon neutrino. So we've got this second family. And the only difference is that it's the same particle, the same charge, but it has a higher mass. So this is the muon family, or the second family, if you like. Now, at even higher energies, we get even more massive particles. And this family is called the tau family. TAU. So it's like family 3, or tau electrons. And the tau symbol is a sort of T shape. A lot of these letters are Greek letters. Once again, we get the anti-tau neutrino. And we have the anti-particle version of the tau, which is called an anti-tau. And in its production and decay, we get the tau neutrino as well. So we've now got, if you add them up, we've now got 12 particles, 6 particles and their antiparticles. There's the particles, there's the antiparticles, and their associated neutrinos and antineutrinos. Now, these are all fundamental particles. And by the end of this, you should really have this table drawn out. Of these different particles. These 12 particles are all collectively known as leptons. So this is the normal energy, higher energy, more massive, even higher energy, more massive, naturally occurring. Some of these are naturally occurring in high atmospheric cosmic ray collisions, and these ones really are only ever seen in particle colliders that we build. So that's this first bit about fundamental particles and an introduction to 12 particles that you need to know the names of and the symbols and their antiparticles, and some of them are neutrinos, some of them are antineutrinos, and so on, but they all form this group called leptons. And that's the end of this short little lesson.